Okay, so this is the solution for Spring 2008 Physics 101 Midterm 1 question 1. We're asked to consider two objects A and B moving with constant acceleration on a plane, which means this is a two-dimensional question. So if it's constant acceleration, I can separately use constant acceleration formulas for the position of A and B, X component and Y component, all of them separately. So let's start with the properties of A. At time t equals to 0, apparently it's at 0, it's at the origin. And its initial velocity, VA0, is 30 I hat plus 40 J hat meters per second. And its acceleration, both objects have the same constant acceleration, so A is just minus 10 J hat meters per second square. Based on this, I'm given the initial position, I'm given the velocities, initial velocities, and the constant acceleration. I think I should be able to write the x position of the particle as a function of time. Initially, and I will always use, that was the one-dimensional formula, x0 plus v0 t plus 1/2 a t square for each component of each object separately. So let's start with the x position of object A. It's at the origin initially. Its velocity is 30, initial velocity is 30 meters per second along the x direction, and it has acceleration is 0 in the x direction, so that's great. xa of t is 30 t meters as a function of time. How about ya of t? At 0 because of the origin, it has a velocity of 40 meters per second, the initial velocity, but there's an acceleration of minus 10 meters per second square along the y direction, t square. So y of t is 40 t minus 5 t square expressed in meters, which means I can actually find RA. Well, let's write these later. Let's do the same thing for XA, XB, the same thing we did for XA and XB, XA and YA for XB and YB. XB initially it was at 20 meters, right? And its velocity has no x component, so no initial velocity in that direction. It doesn't have any velocity acceleration in that direction, so for all times xb of t is 20 meters. How about yb of t? Initially yb is 0, its velocity along y direction is 50 meters per second, and its acceleration is minus 10 meters per second square. So yb of t is 50 t minus 5 t square meters. I am asked to write the position vectors for A and B separately, and now that I have found the components, I can easily do that. This is going to be 30t I hat plus 40t minus 5t square j hat, and I must always supply the units. RB of t is 20 I hat plus 50t minus 5t square j hat, again in meters. So I have expressed the position vectors of A and B as functions of time, so we did this. What's the average velocity of the object during the time interval from t equals 0 to t equals 2? So let's first see where this particle is at time t equals 2, it's at 60 I hat plus 80 minus 20 j hat meters, which means this is 60 I hat plus 60 j hat meters. Initially at t equals to 0, it was at the origin, right? So what's the average velocity? It's a vector. The final position minus the initial position divided by the time that passed to go from initial position to the final position. So this is going to be delta t is here 2 seconds, so this will be 30 I hat plus 30 j hat meters per second. That's great. What's the maximum y coordinate of the object B? Okay, so I can see that yb of t is 50t minus 5t square meters. How do I find the maximum of any function? I take the derivative with respect to time. Let's carry out the derivative. First term gives me just the constant, second term gives me t squared is 2t, then the derivative is taken, so minus t, and if I equate this to 0, I find the time at which this function is maximum. So what I will find is t max is 5 seconds, so yb t equals t max is 50 times 5 minus 5 times 25. This is 250, this is 125, so it's going to be 125 meters. Okay. What's the velocity of object A relative to object B at time t equals 2 seconds? Now, let's find the velocity of object A with respect to the ground first. Okay, we have written everything with respect to ground, so dr dt above should give me the velocity of object at all times, and if I take a derivative, the x component is giving me a constant. How about the y component? I'm doing the derivative really fast. 40 minus 10 t j hat meters per second. How about vb? It's going to be the derivative of the position vector of the second object. The first term gives me 0, it's a constant. The second term gives me 50 minus 10t meters per second. What's the relative velocity of A with respect to B? Well, that's easy. If they were moving with the same velocity, I would see 0. So the relative velocity, which we call VAD sometimes, should be the velocity of A with respect to ground minus velocity of B with respect to the ground. So if I subtract these two, I will find 30 I had minus 10t is cancelled, minus 10 j hat meters per second, and amazingly it's actually independent of time. So at t equals 2 seconds, it's the same thing. So that's what we have found. How about E? What does question E ask? What's the distance between the two objects at time t equals to 1 second? Alright, so RA at t equals to 1 second. Let's check what it is. When I put t equals to 1, RA is 30 meters I had plus y component is 40 minus 5, 35 meters How about RB at t equals to 1? The x component of b was always 20. The y component is 45. Okay. Plus 45. J hat, right? 45 J hat, yes. So RA minus RB is a vector. Both of these are in meters. So RA minus RB is 10 I hat minus 10 J hat meters. But I am asked to find the magnitude of this vector, which is going to be square of both components square root, which will give me 10 square root 2 meters. All in all, quite lengthy but straightforward question.